Hmm. Sorry, I was trying to, like the book I was looking at, it doesn't quite it doesn't quite say. I think though, if c is not equal to 0, then f of infinity should be understood in kind of like, think of it in the limiting sense. What would you think it should be equal to? No, not 1.
A over C.
A over C, right. And I said that this, there's something left to be said in my definition as well, isn't there? Come on, guys! Like, what? You guys don't let me do this. Can this formula be defined for any z and c? I mean, is there a problem there? Maybe. We can't have c and d both 0. That would violate the ad minus bc not equal to 0 condition. But your heart's in the right place. Yeah. So we need z not equal to what? What, minus d over c, right? For c not equal to 0. So it's a little bit of a word salad here, all right? So like, great. So, oh man, I'm trying to follow Gamelin, and I love Gamelin, but so what's the definition? You just have f of z is equal to like az plus b over d, if you will, for all z and c, right? And so like if this is the case, if we're in the c equals 0 case, that's how we define it on c. And we also say that infinity maps to infinity, all right? So that's the c equal to 0 case. C not equal to 0 case, we use the fraction, except at the pole, right? And we map infinity to a over c. There's one last thing to cover. So in the case c not equal to 0, I've told you, when we're not at the pole, we use that. When we're at infinity, we do this. What's left to talk about? Minus d over c itself, right? So in this case, what is f of minus d over c equal to? I mean, this is the definition. We're defining a function from the extended complex plane to the extended complex plane, which, I mean, come on, we should put what? We should put infinity here, right? That's where the pole goes to. Okay, so now I've given you the complete definition in the case c not equal to 0, and then over here in the case c equals to 0. And so let me divide. I guess if I was going to draw some kind of dividing line, like here's the c equal to 0 stuff, right? This is all c equals to 0. And then everything else is the c not equal to 0. All right, are we understood? Do you guys got me? Okay. You can find a way to write this in a more organized and less hideous fashion. Yes? Sorry, it's bothering me. All right, so that's what it is. But what is it? What are fractional linear transformations? So let me show you a little bit of algebra here. First of all, are they invertible? Like what if I put W is equal to AZ plus B over, okay, so let me flag on the play here. We really oftentimes need to break up into the case C equals to 0, C not equal to 0. So like, if C is equal to 0, if C is equal to 0, we're in the affine case. And in other words, what are we looking at? AZ plus B. Well, AZ plus B, that's a pretty easy function to think about, isn't it? What is that? What is AZ plus B? So the affine case, we have f of z equals to AZ plus B. Did you see what I did? I just went ahead and I put the D. I know D is non-zero because I can't have both C and D equal to 0, as Jeff taught us. And so I can just as well roll the D into the definition of A and B, and that's my arbitrary, like affine one. Can you invert this where A is not equal to 0, right? Because if A was 0, we're in trouble. If C is 0 and A is 0, again, we can't have that. So A is not equal to 0. And so can we invert this? Can you find the inverse function in this case? How do you find the inverse function? What do you do? Finally. What's that? Set equal to the, no! Come on, man. See, this is what's totally wrong with the way we teach pre-calculus. You should have always been taught to find the inverse function, you write down y equals f of x and you solve for x. That's all you do. You write down the formula and you solve for z. That's the inverse function. So like, I solve for z, w minus b over a, that is f inverse of w. So is the inverse of an affine transformation an affine transformation? Looks like it is, right? Because if I change the letter, f inverse of z, you got what? 1 over a times z minus b over a, right? That is, again, an affine transformation on the complex plane. So apparently the inverse of an affine fractional linear transformation is, again, an affine fractional linear transformation. You guys like group theory? Yes? You don't know? Oh. So who doesn't like group theory in here? Well, you haven't experienced it yet. There's this thing called a group in group theory. The set of affine transformations forms a group. The identity in that group is literally this guy. The identity transformation. That's a fractional linear transformation. If you compose that with any other fractional linear transformation, you get the same one back again. It serves as the identity for this group of transformations under composition. And what this little calculation shows you is that if you were to look at the subgroup of affine transformations, well, it's a subgroup because the inverse of an affine transformation is an affine transformation. And it's easy enough to see that if you compose two affine transformations, you get another affine transformation, right? Like if I have f1 of z is like a1z plus b1, and f2 of z is a2z plus b2, and I look at the composition of these guys, what do you get? It's an affine transformation. So the set of affine transformations forms a subgroup of the set of all fractional linear transformations. Well, that would only make sense if the set of all fractional linear transformations was itself a group. All right, so I've showed you that we can find the inverse in the affine case, but you know what? We can still find the inverse in the C not equal to 0 case as well. So you guys solve it for me. You want to solve W equals to AZ plus B over CZ plus D, C not equal to 0. Solve for Z. Can you do it? Come on, you can do it. You can do it. I hope you can do it because like a lot of the algebra in this part of the course is basically this algebra right here. Solve for Z. You say you can do that, right? Come on, we can all do this. So we got ourselves a WC minus A times Z is equal to B minus dW. So I get myself a Z is B minus dW over WC minus A. Lo and behold, F inverse of W is equal to B minus dW over WC minus A. Or if you prefer, I can tell you that this has inverse, F inverse of Z. We could write it as minus dz plus b over cz minus a. Let me check my work for a second here, guys. Yep. So as you can see, it's another fractional linear transformation. In fact, it happens to also not be affine, right? I guess technically speaking, I should also fuss with the what happens with infinity in the pole, right? But you can check that that all sorts out as well. All right. Any questions so far? All right, so here's the really cool thing, is you can take one of these Mobius transformations, all right? And by the way, you can compose a Mobius transformation with a Mobius transformation, all right? And if you compose two of these together, guess what? The same thing happens with the affine case happens with the non-affine case. You'll again get the composition of two of these is another one of these as it happens. Maybe we'll do that next time. It's actually really interesting, the calculation. But I just want to get to the main point here before we end today, which is if we look at, let's see here, Z maps to Z plus B over A maps to A times Z plus B over A. What's that give us? That gives us AZ plus B, right? But we can also look at Z maps to Z plus D, and then we can map that to 1 over Z over D, Z plus D, and then we can map that to B minus AD over Z plus D. And then we can map that to A plus B minus AD over Z plus C, Z plus D, right? And you might recognize that this is equal to what? This is equal to AZ plus B over Z plus D. So what am I doing? Let me try to explain the logic of why this is what we're doing is interesting. First of all, start out with, you know, AZ plus B over CZ plus D. We can say, you know, we can set C equals to 1 without loss of generality. Why is that? Because if C is not equal to 0, we can divide by C, and we can force the coefficient of Z to be 1. Okay? So what's the nature of these transformations I'm talking about here? Let me write it out. What are we looking at? This is a translation, right? This is a dilation. A dilation is a multiplication by a non-zero or possibly zero complex number. Okay, well, I usually think of A as being non-zero here to make it interesting. Okay, that's a dilation, which we know is what? It's a rescaling and a rotation by the magnitude of A and the angle of A, right? First week of the course we learned that. What are these? Translation. Ooh, what's this? This one is the interesting one. This is inversion. Inversion. And what are we doing here? Dilation. And again here, translation. What does this show? This shows that, and of course, by the way, the affine transformation, right? Z maps to AZ plus B. That's what? That's a translation and a dilation as well. So every single Mobius transformation can be built as a composition of successive translations, dilations, and inversions. Right? That's what this calculation proves. Okay, what happens to circles? What happens to circles and lines under an affine transformation? If you take a circle and you shift it, you translate it, still a circle. You take a line, you shift it, still a line. You take a circle, multiply it by a non-zero complex number, still a circle, easy to check. You take a line, multiply it by a non-zero complex number, still a line, easy to check, right? So dilations and translations map circles to circles. That would have been a lovely, simple homework problem that a more reasonable instructor would have assigned you. But what did I do? What did we all suffer through? We suffered through proving that inversion maps lines and circles to lines and circles, especially when we extend the meaning to the Riemann sphere. As we can, we're defining the fractional linear transformations on the Riemann sphere here, actually. That's what the extended complex plane is. So what does this all mean? Oh, this means that a Mobius transformation maps lines and circles to lines and circles. So then, what if we talk about a half plane? What is a half plane?
It's half of a plane.
It's half of a plane. Very good, Anthony. It's many lines.
Or many circles.
So what is a Mobius transformation going to do to a half plane?
Map it to a half plane.
It's either going to map it to a half plane or it's going to map it to circles. Well, no, but remember that generalized circles, it's either, so if these all get mapped to circles, it might map this to one of these deals. And that's what we're going to explore, like next class, is how fractional linear transformations are natural maps to take half planes to open disks and vice versa. What's beautiful is there's a theorem that if you pick 3 points in order, then you say where those 3 points have to go also in order, that uniquely defines a fractional linear transformation. And there's an algebraic device to calculate it, something called the cross ratio. But anyway, we can do more simple things. We should also talk about something else called the Riemann mapping theorem, which says that if D is a simply connected domain in the complex plane, then D is not the entire complex plane, then there is a conformal map of D onto the open unit disk D. And essentially what we're doing is giving examples of that. Anyway, more next time. Thank you, thank you.